Okay, next lecture, Adrien Taylor from India postdoc, yes?
Yes.
You work with Francis Bach at the moment, and as far as I understand, you plan to talk about joint work with Francis?
Joint work with a few people, but I will come to that.
Okay,
Don't worry.
Okay.
Thanks.
It's a very perspective direction in modern optimization. I strongly recommend to pay attention to this talk because, in my opinion, it's one of the most interesting things that happens in the last few years in convex optimization.
Thank you a lot, Sasha, for the nice introduction and for having me here. So just before starting, please feel free to interrupt me. I don't plan, well, I have too many slides. I don't plan to make them all. So I prefer having like everybody, or at least most of the people, remembering something from the presentation than having, done all my slides. Okay? So this talk will be essentially focused on, essentially how can you use your computer in order to design proofs for essentially first-order method and mostly in convex optimization. Okay, so before I go into the topic, let me say that I will, essentially it's summarized. I will not go into the details of each contribution of what happened in this quite recent field. But let me say that I will mostly summarize works I did with great other people. So most of the things I will present were done while I was at UC Louvain, and in particular with my two former advisors, so François Gliner and Julien Hendricks. I will also spend a bit of time on things we did with Etienne, and also with Ernest, Carolina, and Pontus. Okay, and then maybe at the end something with Francis also, but it's not sure. Okay. So a second thing, last thing before I begin. So I will not go into the details again on what has been done by who during the presentation, but let me say that this topic started quite recently and there is not a lot of literature on it. So if you want to check what happened, how it started, I would say, essentially I would recommend going through the work of Drory and Teboul, who is quite recent, also 5 years old. So essentially they started this trend. Okay, so there were some other people who also worked on it. Okay, I will not go into the detail again. Essentially, I would say those are the main references in this topic, I would say. So it went further in many different directions. Okay, so essentially you can divide the things in two parts. So, maybe I should have said that in the beginning. So this is maybe a slide that you best look after the presentation if we go to the slides. Okay, so this is not the most informative. I think it's informative once you saw the presentation, just that I don't want to interrupt the flow. Yeah. Okay, so essentially those works, you can rank them categorize them in two categories. So one of them is what we call performance estimation problem. So essentially it will correspond to what I will present. It's an optimization point of view on how do you generate proofs using your computer. And the second one, which is mostly done by Lessard and co-authors, is what we call integral quadratic constraint, and it's based mostly on a control theoretic point of view. Okay, so essentially those are very related, but the way that it is presented are somehow a bit different. Okay, so in this presentation, I will focus on essentially performance estimation problems, so optimization point of view, and through a very biased lens, since I will mostly talk about the point of view introduced together with Julien and François. Okay? And if you want to reproduce anything that happened during the presentation, all codes are online. Okay? And normally I will let the slides free after the presentation. Okay. So far, so good. Okay, so the overall question we want to tackle is essentially, okay, how can we prove that, essentially an optimization algorithm works? Okay, and how can we, yes, so this is the general question. And the overall goal is to be able to somehow automate the worst-case analysis of, convex optimization algorithm, and in particular first-order methods. So I insist on the fact that we are doing essentially worst-case analysis here. So there are other ways to analyze algorithms, which may be more relevant in many different settings. Here we mostly focus on worst-case analysis, which are somehow standard in the first-order literature. Okay, so if I could choose 3 things that I would be happy if you remember at the end of the presentation, I would choose the following. So the first one is that, by definition, when you study worst cases, well, worst case, there are always solutions to optimization problems, okay, by definition. Of course, those optimization problems, they may be, well, not very relevant or not very useful because it may, in general, be difficult to solve them, okay? So sometimes, still, they are useful. And in particular, so this is what I will try to convince you during the next few slides, well, when you consider first method in convex optimization, actually those worst-case computation problems, they are often tractable. Okay? Okay. So the talk will be divided into, so mostly 6 parts, but I think I won't have the time to do those two, sorry. So essentially, I will do everything on one simple example, which is gradient descent. Okay, so everybody knows it, well, I guess. And I will essentially motivate everything I will do based on this simple example because essentially you can understand all ingredients of the methodology based only on gradient descent. Okay, so this is what I will do here. Then I will try to convince you that it's actually more general than just being able, well, it does not allow you to analyze only gradient descent. Okay, so this is the second part. Then I will give a bit more example. So maybe I will go through those two sections, but I'm not sure. And then I will conclude. Okay, so now let me continue a bit first on the blackboard. Okay. Okay, please tell me if you cannot see at the end of the auditorium. Okay. Okay, so, well, usually, so what we start with is basically gradient descent, okay? So let's say we want to minimize some function, f of x over Rd. Okay, so that's the starting point. Let's say that, well, f, let's say that it's in some classes, some class of function, okay? Otherwise, you will be able to say nothing. So is it okay for everybody? Oh, okay, yes. Of course. Well, I will just. Okay. In f of x, let's say in Rd. So we said that f is in some class of function. Otherwise, well, if f is just general, you will be able to say nothing. And then we said that, well, we start by saying, okay, we want to study the performance, to start with, of gradient descent. Okay? Some step size, and then f prime. Okay, so what we want is, essentially, if we run this algorithm for a few iterations, we want to be able to say, okay, what's the quality of the solution I end up with, okay? So the word quality, it can have like many different meanings. So for example, a standard thing to do is to try to say that, well, if we apply any iteration of gradient descent, well, what is the best thing I can say on this thing, for example? Okay, f star is the optimal point, the optimal value. So for example, one thing we could want to have a guess for is, well, what is the best possible guarantee I can get on this thing? Okay, so we want essentially to bound that. But you can change that. So for example, you could be interested instead in having like the last iterate close to an optimal solution. This could be something else. Okay, this is a matter of choice and application. And another thing is, for example, you may want to have a small gradient. Okay, this is a matter of choice. We'll pick one. Okay, I pick one randomly. Well, do you have a preference? Or let's say first one, so that it's easier to erase the others. Okay, so let's say first one. Okay, so I will erase this thing. Okay, so if I want, I will put it on the other side. If I want to obtain so the best, well, a guarantee on this thing, what is the best thing I can do? Well, essentially, the best guarantee I can get is essentially this thing, the solution to an optimization problem, which is like this. Okay, sup over f. Okay, so f, now I'm looking on the worst possible problem, okay, of this thing. Okay? And the constraints are the fact that, well, my problem, it should be in the class of function I've been considering in the beginning, because those are my assumptions. Okay? And, well, I want to study gradient descent, right? So here I also have the iterates. So here I have to impose the fact that I generated the iterates with gradient descent. XK. Okay? So just the base thing. This is essentially just, well, the best thing I can do, the best bound, right? It is the generic way I could obtain an upper bound on that for all, which is valid for all f in the class of function I'm considering. Okay? Does someone have any clue on the optimal solution value of that problem? No? Is there something missing? So actually, there is something missing. So the optimal solution, well, value to this problem, in fact, it's unbounded. Why? So first, well, I have to maybe restrict it to a class of problem that may make sense. But usually, also, here I've let the initial condition free. So usually, if I let the optimal solution free, the initial solution, well, initial guess free here, well, I can choose it arbitrarily bad. So it means that the solution to this problem can be arbitrarily bad. Okay? So usually, what I have to do is to add an initial condition. So an initial condition, again, I can add it in many different ways, and maybe it will ring a bell to some of you. The standard way to do it is actually to do that. So to say that this is bounded. Okay, it's bounded by some constant. Okay, so this is a standard way to do it, but you could change it also. You could say, okay, my starting solution is not too far away from the optimal solution. For example, in terms of the objective value, it could be like that. Okay, so I'm not too far away in terms of the objective value instead of this one, or I'm not too far away in terms of gradient norm. Okay, so you could pick one. Again, you could pick others. It's just that if you take a stupid one, the result of this optimization problem, it will be silly also. Okay, so it can be unbounded if you give it something which doesn't make sense. Okay? Okay, so essentially this is all I will gonna be talking during this presentation. So if there is any question, please don't hesitate. I will re-go through it on the site, but so this is what we're gonna do. Okay, so maybe one motivation. So why do I want to do that? So what I want to provide you is a tool that allows to generically analyze optimization algorithms. So essentially, if you formulate the fact of, while computing the worst case of your favorite optimization algorithm as an optimization problem, well, if you can reformulate this problem in a tractable way without any, if you can solve this problem, essentially, it allows you to have like a generic methodology for studying your favorite algorithm. Because essentially, if the solution to that problem is silly, it means that you will never be able to have a non-silly guarantee. Okay? So this is the starting point. If the solution to this problem is bad, then you cannot prove something better. Yes?
A couple of clarifying questions. So this
yes?
one, where does it enter anyway, the conditions?
Sorry, which F1?
Is it F1 or no? It's a comma over...
Oh, it's F. Sorry, it's a comma. The variables are both F and the iterates. But I can just put a space in between if you want. It's just not, okay. It's not F1, it's just F. Okay, so it doesn't seem to clarify. So what I want is to find the best possible guarantee for this thing without, such that, if I blindly apply gradient descent on this a function f, which is in some class of function, I want to know in advance whether this is going to be working or not. So for doing that, I try to find the worst possible problem instance for gradient descent. So this is essentially the question. And so the problem instance is essentially, the worst possible function. Okay?
So you basically want to find the worst function from this class for
yes.
a given optimization object?
Yes, this is all of it. Okay? Then, of course, I'll have to specify the class, and I have to specify the algorithm, and then I have to specify a bunch of other things, like what I want the guarantee on. So for example, on this value, what are the initial conditions, and those are all degrees of freedom you can play with. But the overall thing is that, well, the best guarantee you can get is, for a given criterion, is the one you would obtain by solving the corresponding optimization problem. Okay?
And
Yes?
another question is F star. So you'll be assuming, so that's a ground truth, and you assume that you have it?
Okay, so F is in the variable. Here, here I should have said that usually what I do is I assume that the class of function is convex. So for having F star, I assume that essentially, so I have some X star which is also in the variables, and I assume that F prime of X star is equal to 0. Okay, normally it should be more clear through the slides maybe, but so really the thing you should have in mind is the fact that F is in the variable, and F star is also therefore among the variables. Okay.
And can you also give an example of a class of functions where this type of problem would have a sense?
I will do it. Don't worry. So this is a general idea, and then you have to specify the ingredient in order to make sense of out of it. Okay? Okay, let me go back to the slides. Okay, so now we do the same thing. I will do it, but I will do it for gradient descent, so again, and I will specify the class of function we'll be working with, which is now smooth strongly convex functions. Well, class of smooth strongly convex functions. This is for the sake of the example. You can do it with other classes of function afterwards. We'll do it, okay? So we want to minimize f, which is smooth strongly convex. We said that we use gradient descent, okay? And what we want is to be able to guarantee something on the last iterates of gradient descent. So essentially, we want to be able to say something about one of them, okay? Okay, so well, everybody knows what a smooth strongly convex function is, or no? I can go through it in 1 minute. If no answer, I do it. Okay, so if you consider the blue function, okay, we say that essentially it's convex if when you do a first order development around every point, like the red one here, you get a global lower, underestimation of the function, which is linear. Okay, now we said that it's strongly convex if when you add a bit of curvature on this first order development, curvature mu, it remains a global lower bound. Okay, so that's for strong convexity. For smoothness, usually we require that we said that the gradient satisfy Lipschitz condition. Okay, what we'll do here, what is sometimes more useful is to say instead that, which are somehow equivalent, that essentially if you do a first order development around like every point of the function, and you add to it some curvature, some quadratic term, you end up with a global overestimator of the function, which is quadratic. Okay? Okay, so now how can we, essentially solve the problem I showed you on the blackboard for this particular case? So let's fix the things. So I will assume that we'll solve the problem only for one iteration, okay, because it's simpler. And what I want to do is to bound the gradient norm. So what I want to say is I will run the gradient descent for one iteration, and I will try to have the best possible guarantee I could obtain for the gradient norm after one iteration. Okay, so this is the performance measure I will be considering. Okay, so among the variable, I have this f, okay, which is now required to be in the class of smooth strongly convex functions, because this is my assumption. The second requirement is that, x1 is generated from gradient descent. Okay? So, and the last requirement is that I have some initial condition. So here, I will choose this one because it will make the solution easy, but you can choose other ones. So I will choose the fact that my initial gradient norm is equal to some constants. Okay? So what I will try, so first, what are the variables? So f, so the function, I will be looking for the worst possible function, and the iterates, okay, x0 and x1. And what are the parameters? So if you want me to solve that problem, what do you have to provide me with? You have to provide me with a strong convexity constant, okay, the Lipschitz constant, or the smoothness parameter, the step size you are using, and the initial value of the gradient norm. Okay, so if you provide me with that, I can solve this. This is what I will try to convince you during the next few slides. And actually, if you want to solve this, so you have to use, well, to rely on semi-definite programming, and the solution is exactly that. So you may recognize things, well, for those who worked in optimization, you may recognize something here. So essentially, this is what we usually call the convergence rate, okay? Okay, so you see that it depends on the step size, on either strong convexity constant or smoothness, and on the initial condition. Okay? And, well, if you happen to solve this problem, actually you also have, so you have an upper bound, the best worst case certificate you could hope for, and you also have the worst case functions. So the function on which your algorithm is working in the worst possible way in the sense of the performance criterion you choose. Okay, and those are one-dimensional quadratics. Okay, this could be expected also. Okay, questions? Yes?
Why do we choose as a criterion for worst performance the maximum gradient of the derivative?
Okay, I have two answers. So the first one is here I just choose it because it's simpler. I have only it less, well, in fact, so this problem is really the simplest one you could expect because you don't have the optimal point as a variable. So it's kind of, well, so the first answer is because it's simple. And the second one is, in practice, gradient norm, if you use dual method, it corresponds to primal feasibility. And so if you use dual methods, actually, you may want to minimize the gradient norm of the, in the dual, because it corresponds to have a good primal solution. Okay? So this is the technical one, but the honest one is really I choose it because it was simple. Okay? Other questions? No? Okay. Let me just try to, well, to explain to you how you can convert that into a semi-definite program. Okay, so the first step is, well, usually when you see such a problem, the thing which may look the more frightening is the fact that we are working with the function as a variable. Okay, so this is an infinite dimensional variable. You may not want to work with that. So this is the first question. How do we treat it? Okay, the second question is, okay, even if we treat that, how can we treat the fact that it's actually, well, the f should be smooth as convex? Okay, so the answer is quite simple, actually. We are doing something quite standard. I will discretize the problem. Okay, so instead of playing with the function, I will play with, well, function discretized at the different iterates. Okay, so actually, I only need 2 points for the discrete version of the function. Well, f1 and f0 and f1, because I'm only studying, well, one iteration. So this is the first thing. I discretize the function value, but I also discretize the gradients. Okay? So I will also need 2 gradients. I will need, as a variable, the gradient at the well, initial iterate, and the gradient after one iteration. Okay, so those will be my variables, sorry. And so how do I take into account this constraint? I will do it in a brutal way so far, well, not for now. I will just require that, well, essentially, if I'm being given a set, well, a discrete version of the function, I want it to be interpolable by a function which is in the good class. So essentially, the new constraint is the fact that there should exist a function in the good class, so in the class of smooth strongly convex function, which explains my data. Okay, so which explains the fact, well, my function values. So that if I evaluate the function at the good points, they indeed give me the good function value. And if I evaluate the gradient of the function at the good points, they indeed give me gradients. Okay? Okay, let me put that into the previous problem. So if I retake this problem, so the reformulation I propose is the following one. So you add as variable f and the 2 iterates. Now I propose to do like this. So we'll just rename the variables. So the gradient norm after one iteration, we called it G1. Okay? So this is the objective. Now the variable f and this constraint will handle this way. We'll handle it this way. So we'll require that there exists f in the good class of functions such that it explains my data, the discrete version of my function. So this is my second constraint. My third constraint is, well, I still want x1 to be, well, generated by gradient descent. So this is just this constraint, which is rewritten. And I still want to impose some initial condition. Okay? Okay. Yes?
So transition to from general function of degree of freedom to those functions and derivatives at a particular
point. It's clear, but it's not clear why this existence.
Okay, I agree. So actually, it's just a transition for the next point. But I agree. No, here it's not better because you replace it by an ugly constraint. I mean, you don't have the infinite dimensional variable, you have an infinite dimensional constraint, so it's not better. I agree. So how do we deal with that? So for this part, you will have to trust me a bit. Okay? So just before going into the next slide, let me just mention that here now the new variables are the two iterates, the two gradients, and the two function values. Okay? And what we want to make disappear now is this thing. Okay? So how do we do that? So let me reformulate the problem again. So we are given coordinates, so the x. We are given slopes, so gradients, and function values. Okay? And now we want to ensure that there exists a smooth strongly convex function which explains my data. Okay, so how can I do that? So for that, you'll have to trust me. In fact, this can be expressed with a quadratic constraint. Okay? This is the part I think I won't explain, but if you are interested, this is quite easy actually to show, but we can do it offline if you want, or if I have time, but I think I won't. Okay, okay, maybe just a bit of intuition. If you forget about these things, this is just the regular definition of what a subgradient is. So if you were working not with smooth strongly convex function, but just with convex functions, this would be expected. Okay, this is just convexity. Okay? Okay. So let me just put that into the problem. So again, we had this problem. So now we have to impose the fact that for every pair of points, okay, we add this constraint instead of the existence constraint. Okay? So just to give a bit of insight, in fact, this is still not better. It looks better because it's a quadratic constraint, but actually it's a non-convex quadratic program. So yes, and yeah, okay, so it's non-convex. Why is it non-convex? Actually, it's non-convex because of this term. So this is in fact convex, this is convex, so, well, and this is convex in terms of f, so this is convex in terms of g and x, but this is not, okay? If you have x times y, it's not convex. So it's a product of variables. Okay. Okay, so the thing is, so it's non-convex, and the problem with non-convexity here, well, actually, it's not really a problem that it's non-convex. The problem is that, well, if we solve that problem to local optimality, well, it's not a guarantee. So we want a guarantee on the performance of gradient descent, right? And so if you solve that only locally, well, it's not a guarantee on the performance of gradient descent. So if you could find something around in order to get guarantees from this problem, even if you don't solve it, you would be happy. Okay, so the way I propose to proceed is by actually solving this problem using semi-definite programming. Okay, and for that, I will introduce a few other elements, but I will only do it if there are no other questions. So far, so good? Yes? Okay. Okay, so how can we deal with that? So we will use something which is standard in the semi-definite, when using semi-definite programming, we'll use what we call lifting. So what we'll do is, well, just to summarize the previous problem, the problem was coming from the scalar product, so the product between the x and the g's. Okay, so what we'll do is, first, a bit of notation. I will create a matrix in which I will put like all elements that are supposed to be in RD. So coordinates, so the x and the g's. So coordinate and gradients. Then, okay, let's not care about the dimension so far, well, for the moment. So what I will do is introduce what we call the gram matrix, so matrix which contains essentially all scalar products. So this matrix, I call it G, and in fact, you can obtain it just by doing P transpose P, with P being this matrix. Okay? And now the thing is, well, actually the previous problem, it's linear in terms of the entries of this matrix. Okay? But we lost something. Okay? I will explain what we lost. So the thing is, well, if you find a solution to the previous problem, you can transform it to a solution to the previous problem formulated in terms of the gram matrix. But if you are given a gram matrix, a positive definite matrix, G, then it may not always be possible to recover a solution to the previous problem. And why? Because actually, so this is, well, standard tool in linear algebra. It's called Cholesky Factorization. Essentially, it comes from the fact that if you have such a P, Well, actually, it will lie in it's a matrix of dimension d times 4, right? So it means that when you do this operation, so P transpose P, you will end up with such a matrix, but it will be at most rank d. Okay? So this is what is written here. And the thing is, so you have to impose the fact, so if you want to find the worst case given a certain dimension, you have to impose a rank constraint. Okay? And a rank constraint, in fact, it makes it equivalent to the previous non-convex quadratic program, which means that actually semi-definite programming, it's with rank constraint, it's also NP-hard. Okay? So you may not want to deal with that neither. But the thing is, actually, you can remove these constraints just by doing an additional assumption. And this assumption is the fact that while you are also interested in worst cases when the dimension is higher than 4, right? You want worst cases that are valid for all dimensions, so you can just think of removing these constraints. Okay, so just as a summary, so you can reformulate the previous problem as SDP, but if you do so, essentially the solution to this SDP, it will provide you with the best possible guarantee that does not depend on the dimension. Okay, and not depending on the dimension, actually this is usually what we want and what we achieve in first-order methods. Okay, so this looks strange, but actually this is just recovering standard stuff, standard things, let's say, from another point of view. Okay, questions? I will go through examples if you have the impression I lost some people. Okay, so what can we do? So, well, essentially, if you fix, so again, you give me the parameters of the problem, so give me strong convexity, the smoothness constant, the value of the initial condition and the step size, okay? I can take care of imposing, so this is like technical semi-definite programming stuff. I can put them into whatever solver, okay? I set up everything, and essentially, if I solve it, so let's say you gave me those values, well, the computer is able to solve that, okay? This is, well, just using standard solver again, and it will give you a numerical value for the worst case, okay? So using those values, I can certify that, well, the computer certifies that you will never be able to get a worst case bound which is better than this one. Okay? Okay. So this is numerical. So usually we are not totally satisfied when we end up, well, with a numerical value because, I mean, this is something which may not be practical in many situations, only this thing. Okay, so can we go into can we get like analytical guarantees on this behavior? So that's the next question. If I don't have question on this. No? Okay. So, so for solving these kind of problems, so don't worry too much. This is just the previous problem that I've put with semi-definite notations. So this is exactly the same. You should not look at it in another way. Okay, so the thing is, for solving the solvers that actually solve that kind of problem, usually they rely on Roland speciality, which is interrow-point method. And in particular, you can use primal dual interrow-point method in order to solve that. So the nice thing is, well, you will at the same time recover a primal solution, okay, which corresponds to a discrete version of the worst case problem, okay, so the worst possible problem instances. And at the same time, you will recover dual variables. And so the thing is, dual variables, actually, they matter a lot in that methodology, and I will explain why on the next slide. So the thing is, in order to obtain analytical guarantees, this is exactly what we'll be using duality, essentially. Okay, so this is what I will try to convince you. Okay, so essentially, the computer, you will give him like this SDP, and the answer it will give you is essentially that, so it will provide you with a discretized version of one of the worst case problems. And it will also tell you that, okay, in order to prove the result, you only need to combine this inequality with this inequality, and you can generate a proof with that. So for that example, what does it give? Essentially, it will tell you that in order to prove the result from the first slide, you only need those two inequalities, and that there exists a proof that only consists in summing them and reformulating this sum. And so the proof can be as follows. So you have to find the analytical solution to this, but that's for another part of the talk. So essentially, what it means is that, well, essentially, if you do that inequality times this thing, plus that inequality times this thing, you can reformulate it, and you'll have to trust me on that. This is easy to check, by the way, but you can reformulate it exactly as this inequality. It appears that this thing, well, since I assume something on the step size, this thing is positive, so you can remove it, you can discard it, okay? The inequalities are going in the good directions. And so it leads you to this guarantee, okay? So the nice thing is really that actually this is, so we discard it, but actually we could discard it because, so in semi-definite terms, this is what we call the primal dual gap, okay? This is a bit technical, but still. And since, well, in those problems, you can prove relatively easily that the duality gap is always 0. So you lost nothing by essentially putting it away, which means that automatically this thing will be tight. Okay? And actually, it's tight on the one-dimensional function I gave you on the first slides. Okay? Looks reasonable. You can trust me, or is there something a bit weird here? Yes? So it's a primal dual gap. So it's the difference between the optimal value of the primal and the optimal value of the dual. Okay? But yeah, there are simple conditions that allows you to say that there is none in those kind of problems. Okay? Questions? No. Okay. So let me give you a bit of overview on what we can do with that beyond just gradient descent and smooth strongly convex problems. Okay, so if I have to summarize first what we just did, well, I have to say essentially 3 points. So the first one is, well, the fact that when you solve that kind of problem, essentially every primal solution, it corresponds to a worst, well, one of the worst possible problem instance. Okay, so this is about primal. Now, dual solution, in fact, they correspond to worst case guarantees. So they correspond to proofs somehow. And actually, you can solve them using semi-definite programming. So you can solve them, both of them, at least numerically. Okay? So how can we generalize that? So I showed how to analyze gradient descent for smooth strongly convex minimization. There wasn't even any constraint on that, so it was kind of loose. So let me say that, in fact, well, usually in convex, in convex optimization, the way we encode, well, at least first order methods, the way we encode constraint is through, well, the summation of two functions, one of which is an indicator function, so which is essentially 0 on the constraint set and plus infinity outside. Okay? So usually we formulate it like that. And actually you can, the framework allows you to, in fact, to handle like as many functions in that sum as you want. You just have to add infinite dimensional variable, which you have to discretize after. Okay? So well, the only cost of that is, well, increasing the size of the semi-definite program. Okay, so what can we do with that? So I showed how to encode smoothness and strong convexity, so smooth strongly convex functions, but actually it's even simpler if you don't want them. I mean, if you want just convex function, you actually, well, you can just do it by getting rid of the terms I showed in the beginning, okay? So it's even simpler in terms of inequalities, but you can do also, like, for example, smooth function without strong convexity and things like that. Okay, you can also encode indicator functions, so which are used for encoding constraints, support functions. It also works actually for non-convex functions, well, smooth non-convex functions. And, well, essentially, it works as long as you can put the inequalities, so interpolation inequalities, I would call them, into a semi-definite program. And so, for example, it works also in settings which are not optimization related. So, for example, in monotone inclusion problems. But I will not go into the details. Okay. Okay, so what types of algorithm can we do with that? So, well, essentially, what's allowed us to do this discretization and to solve the problem for gradient descent was the fact that actually, well, I assumed that I was given the step size. Okay, so as long as well, you provide me with the step size, well, they can be varying if you study n iteration, but you have to provide me with the step size in advance, while I can apply the procedure. And it's actually, well, it's restrictive, but it's not as restrictive as it looked, because in convex optimization, and in particular for first order method, it's often like that. So for example, you can do gradient descent, but you can do also subgradient methods. You can do inexact gradient methods. It works just in the same way. Proximal methods, in fact, just correspond to implicit gradients. So it just, again, the exact same procedure. You just have to write the algorithm a bit differently, but it works. Also, conditional gradients, so well, also known as Frank-Wolf, things like that, they all work. Okay? So the only thing is, well, depending on what you want to study, actually, it may well, create a larger or more difficult semi-definite program. Okay? So this is what, I'm not claiming that the SDP is easy to solve. I'm just claiming that all of them, you can formulate them using SDP without any loss. Okay, so this also includes accelerated gradient method, for those who wondered. Okay, so this is when you are given the fixed step. If you're not given steps, well, you can usually do something, but it will not be provide you with exact worst case, well, the best possible worst case certificate you can hope for. Okay, and so, well, in some of the settings, again, the SDP scale badly. So, for example, if you want to do stochastic methods, it's not as easy. Okay. Okay. Let's talk about another way to generalize a problem. So I talked in the beginning about the way you could the way you would like to the way you could specify the preference measure. So you may want to have guarantees, for example, in terms of function values, but you could want them in terms of distance optimality or in terms of gradient norm, for example. Well, all of them, you can just use them because they just fit directly into the SDP. You just have to change the objective. Okay? And this is the same for the initial condition, by the way. So those are natural ways to extend the result. But in fact, there are methods which are non-monotonic, so you may not want to study each time the last iterate. You may want to study the best iterate. And so, for example, it's the case when you use a subgradient method, but you can also do it just fit perfectly into the framework. And again, you just have to put concave functions, which are concave function of the function values and the entries of the gram matrix, and it perfectly fits into the thing. Okay, so far, usually people think that, okay, this is relying on semi-definite programming, so the code for generating the proof should be like a big mess. So because of that, essentially, we made up a toolbox which allows just to avoid those modeling steps. Okay, so we called it Pesto. And so the idea is really that, if you want to try the methodology, you don't need to put your hand into dirty semi-definite programming stuff. It just will do the job for you. And let me give a quick example for that. So let's say we want to minimize the function f, which is assumed to be convex and smooth. You just want to use an algorithm for doing that. The only motivation for the following algorithm is that I don't know the answer. Okay, so I just wanted the SDP to give me the worst case. So I will use fast gradient method. But for doing that, I will replace the gradients, okay, of the fast gradient method by an inexact version. Okay, so I will just replace that. And I use some relative inaccuracy criterion. Again, this is just for the sake of motivation because I don't know the answer to the behavior, the worst case behavior of fast gradient method for that. So what does the code in Pesto look like? Well, essentially, it's about that. So don't worry about the reading it. Essentially, the important thing is that, well, in fact, Pesto just requires you to encode the algorithm as you would have implemented it in MATLAB. Okay, so it just requires you to write the algorithm, no semi-definite program, and then you just have to run the thing. Okay, and if you run it, in that case, you will receive like numerically the worst case certificates on the function values. You can run it for different value of the iteration, for different value of the precision, and those give you like the best possible bound you can hope for. So again, why am I interested in best possible bound? Well, essentially, it means that if you have a theoretical guarantee that you proved, you want to test whether it's good or not, you can just compare it to that. And if you are far away, it means that you can improve it. If you're not far away, then it means you could be happy with it. Okay? And if you cannot prove anything, you can just run it, see if the thing you are trying to prove is actually provable or not. Okay, so, okay. So just as advertisement, this is about 20 lines. Okay, it took me 10 minutes to do, and it gives you the way to prove thing. Questions? Yes?
Does the system provide an example of such function?
Okay, so the thing is, the example is not unique. Because, if it was unique, it would mean that the original optimization problem class was easy, because it means you could, from a few points, determine all the functions going to those points. Okay, so it's not unique, but you can reconstruct one. So we provide a way to reconstruct some worst-case example. But so what the toolbox gives you is a discrete version of the worst case, okay? Which can then be used to reconstruct continuous example if you want. There are constructive procedures for doing that. So actually here, I just took the function value. So in fact, yes, I used the discrete version. I took the function value at the last is rate, and I plotted it. So this is what I did, yes. Yes?
Just want to ask, how complex can these algorithms be that you can replace? So that you need to have fixed
Step size? Okay, you so.
It will not work if we have step size, I don't know, adaptive or Cholesky.
No, so this is actually, we are trying to do that with some colleagues at INRIA, so adaptive step size. So adaptive step size, currently, you can analyze them in a loose way. But actually, when you look at the literature does the same. So I'm pretty convinced that all the bounds that are presented in the literature, that somehow they are like just feasible points to the dual problem, to this one. Okay, so the thing is, so yeah, adaptive methods, they're difficult. But the thing is, so just one thing I want to emphasize is it's fixed step, really in the sense that you have to provide me in advance with the step size. It doesn't mean that the step size have to be constant. And for example, this is not constant step size. Yeah.
But just want to ask, but then probably it's possible to write it inside the method, like the method which has some sub-method inside which finds this adaptive step size.
So you just optimize the number of variables like step size, right?
Yeah. So I mean, is it possible to have just more complex algorithm with finding step size inside this algorithm?
Oh, you mean you want to optimize the step size? Okay, this is coming. But this is not adaptive. This is like optimize step size in advance, let's say. So the algorithm that behaves well, in somehow the best possible way in the worst case. So not always, but in the worst case, they behave. So this is what you well, achieve if you want to optimize the step size. You obtain the best. So essentially, we do it all at once. So we consider like n step of the procedure, and we optimize them. So actually, I say we. So this is in fact why the first slide was interesting. So there is one group which is kind of specialized to. So optimizing the step size, actually, it's a difficult task because it's a min-max problem. So you can think of it as as a mechanic to try, if you give me an algorithm, I will give you a worst case. And then you can try to minimize the worst case as an external, well, you can try other algorithm to try to minimize that worst case, okay? So by updating the algorithm. And so this is in general difficult to do because, well, it's a min-max and it's in the bad direction. But actually there are some people who manage to solve them. In some settings, not all settings. In most settings, it's actually open. But for example, smooth convex optimization, it's totally solved. And I will show the algorithm. Okay? Other questions? No? Okay, then I will go through examples. Oh, sorry. Hold on. Okay, so here it's fixed step. So you assume the fixed step, but you can. So the problem is that the number of iterations you study essentially correspond to the dimension of the semi-definite program. So you have to increase the size of the SDP if you increase the number of iterations you want to study. So there are ways to try to avoid that. So for example, by requiring the proof to be structured. So for example, to have a Lyapunov structure or things like that. So which is essentially what we are obliged to do when we study complicated settings like stochastic settings, but you lose something, you lose the tightness. You lose the fact that it will provide you with the best possible guarantees. But I agree, like looking for the rates instead of the constant with the rates, it's certainly something which is often more interesting than looking to the constant. Yes? So usually we say worst case in terms of expectation. So the worst expectation, yes. But yeah, it depends on the setting you are studying. And if
You might have a very special realization to which what is worst for expectation is not necessarily the worst, right?
So
Meaning of worst is
okay, so if you want, we can take it offline because I don't plan to talk about stochastic, but I have a, I think, good answer for that, okay? Okay, so just let me give a few examples. So I'll start with, no, let me skip this one. Okay, this one. Okay, so let's talk about optimized methods. So if you want, again, I consider like smooth convex minimization. So I want to minimize the smooth convex function, and I'm given access to its gradients. Okay, so it is known that actually, whatever the first order method, you will never be able to achieve something in function values that is better than this bound. Okay, so with the thetas being obtained through that, essentially, this is, you will never be able to beat this thing. So there is no first order method that will achieve for all smooth convex functions something which is better than convergence in 1 over n squared. Okay? So, and by the way, this is quite recent. This is coming from, well, the order of magnitude is quite old, actually, but this clean expression, it's quite recent, and it was obtained through those automated proofs. Okay? So let me give you a few algorithms that actually perform exactly like that. So the first algorithm is something that you absolutely don't want to use in practice. It's a crazy version of conjugate gradient. So essentially, just at each iteration, you perform a span search over all previous gradients. Okay? And if you do that, actually, well, you can observe numerically, and then you can prove that the worst case, well, the best worst case you can hope for is actually this thing. Well, the best worst case certificate you can prove is actually this thing. Okay? Actually, there are other methods which are more practical that actually do that. So for example, if you consider this thing, it does exactly the same. Okay? So again, you can just put that into Pesto. You can verify it numerically, and then you can do the proof by hand. We provide it in the papers. Okay, and then, well, there is also this one, which is actually the algorithm that was obtained by optimizing the step size. So it's called optimized gradient method. It dates back, well, numerically to the gradient table, and then analytically to Kim and Fessler. Okay, and so this is, in fact, really close in terms of shape to Nesterov's fast gradient method. It's just that, well, it was obtained in a brute force way, like optimize the worst case certificate. Okay? Okay, so this is a method. Again, the proofs here, they were essentially computer, I would say, generated, but then you have to, it's not totally generated because you have to transform the numerical solution into analytical ones. So for the next few slides, I will show you convergence guarantee that are absolutely, totally computer generated. Okay? And so I just want to warn you that the expressions are therefore really horrible and quite difficult to pass, but I give them as examples. In fact, I strongly believe that no one could have obtained them by hand, okay? And they were totally computer generated, like using MATLAB and Mathematica. But wow, so they are, I think, not obtainable by hand, but I think they are easy to verify by hand. Okay, I did it, so I'm pretty sure it does. Okay, so I'm not talking about any intuition about those rates. Here, well, really the base point, I would say, well, the point of view I want to defend is really that we are looking at the structure and at intuition of what a proof should look like, but not at all on how the algorithm should behave. Okay, so for the example, I will consider what we call Douglas-Rashford. So don't worry too much about what it is. I will just give you the example, what it looks like for optimization. So if you want to optimize a function of that shape, one way to proceed is to use what they call Douglas-Rashford splitting. So essentially, it's, well, if some people here know about alternating direction method of multipliers, it's similar. So it's assumed that essentially it's easy to minimize H alone without F, and it's easy to minimize F without H. And you can just, by alternating between F and H minimization, you can create well, converging algorithm. Okay, so you can put that again into the framework. And if you do that, well, one way to, well, then you have to choose a worst case criterion. So if the worst case criterion you are looking at is actually convergence in terms of distance between the hit rates, so contraction rates, essentially, well, I will show what it looks like when you study those kind of things. So there are many previous works on that. So one thing I can point to is, well, if you are interested into convex optimization and monotone operators, is the nice work and review work of Ernest Rio and Stephen Boyd. Okay, but this is not the point. So just what does computer-generated proof look like? Well, computer-generated worst-case contraction factors. Well, if you do some assumption on A and B, okay, let's not care too much about what it means. Essentially, you could end up with things like that, okay? I think you agree that it's a bit difficult. So actually, there are many settings for which Douglas-Rashford, it was the non-improvable convergence rates were known. This one wasn't one of them. I think when you look at the expression, you are I think it's pretty clear why it wasn't, right? So, okay, so this requires, so essentially, this is 10 lines in Mathematica. So this is pretty okay, I think. Another one, slightly different assumptions. Essentially, it was also open. And again, I think we can guess why. Okay, so for all of them, the computer provides an example and a worst-case certificate, so proof. And since those are like a contraction factor, actually, those correspond to small semi-definite programs, so you can really solve them analytically. This is what we did. Okay. So, okay, I think questions? Other questions? So if you are interested in the code for generating them, again, they are all on GitHub, and I can comment them while I'm here if you are interested. Okay, so if you want, I can go to convex interpolation, which is the part I said that you will have to trust me on in the first stage of the discretization procedure. Okay, I thought I would not have the time to do it. Maybe I was a bit fast on the other points. Okay, so convex interpolation. Yes?
Just wanted, in the very beginning, you mentioned that there is this control-theoretic approach.
Yes.
So you will be able to comment on that?
Yes.
If you're planning to.
In fact, I'm not planning to, but I can comment on that. So essentially, so in my point of view, well, both approaches are very similar. So the control theoretic approach, in some sense, it's related to this one in the following sense. It looks for Lyapunov functions. Okay, but for Lyapunov function, when the algorithm is converging linearly. Okay, so essentially, it fits well when the convergence of the algorithm is linear. Okay, and when it's linear, they are looking for Lyapunov function certifying that it's linear, and essentially Lyapunov function they correspond to look at the same time for the worst case certificate and for the criterion for which the worst case is the best as good as possible. Okay, so you are actually, so here, if I take back the blackboard. Okay, so let me erase a bit. Okay, so I will put that. So for example, for gradient descent, we showed in the beginning that we had this thing. So with some rho, okay, so this is what I call the convergence rate. And okay, so now the thing is, in the beginning, I said that actually you could change that, right? You could change that. You could, use in the framework, you could use, for example, this thing. Okay, and you can change it here accordingly. And you could also use this one, for example. Or this one, xk minus f star. Okay, so the control theoretic framework, essentially what it does is, it tries to, so it corresponds to the cases where the initial condition, which is this thing, is the same as the final, the thing you are measuring. Okay, so they will be looking essentially for what is how can we measure convergence such that the rate is as small as possible. Okay, so in order to do that, they will instead, so for this problem, what we had was, So we are looking for the sub or the max of, for example, this thing, okay? Okay, here they will say, okay, here I will not consider only this distance, I will consider a family of problems. So for example, I could say it's alpha times distance, but plus alpha times gradient, 1 plus beta, plus gamma times function values. Okay, and well, I have to put the same initial condition here, and they will essentially minimize over alpha, beta, and gamma. Okay, so they will obtain a convergence rate that depends on all of them, well, numerically, on all those things, and they will try to, well, to tweak the convergence measure in order to obtain the best possible convergence rate. Is it clear, more or less? More or less, maybe less. Yes? Some people did it. I did not investigate that. I think it could, but to be honest, I'm interested in more algorithms, so I didn't do it. But I can point you to reference, well, I think there is one who did it mostly. I'm not convinced of the way they did it, but yeah. Okay, so let me go back to interpolation. So again, let me reformulate the problem. Let's say you are given a discrete version of your function. Okay, let's say, so again, coordinates, slopes, and function values for all points. And you want to be able to certify that you can recover a function in the class of smooth-only convex functions such that my data is explained. Okay? Okay, so for simplicity, let's do the simplest case first. So just convex interpolation without smoothness, without some convexity, so that you see what's going on and really the mechanic of it, and you will see that it's pretty simple. Let's take the blue function. Okay, it's convex. Let's discretize it. So let's discretize it here. Well, since we discretize it on those red dots with the corresponding subgradient and corresponding function value, we know that this is true because this is the definition of subgradient. Okay? Agree with that? Okay, so this is well, a necessary condition that, so, well, meaning that every discretization of a convex function will satisfy this thing. Now my claim is that it's actually also sufficient because if you do that, okay, this thing, so the blue reconstruction, well, you have a convex function, right? So it means that those, well, under the condition that this is true for all pairs, well, you can always reconstruct such a function. Okay? So this means that this is a necessary and sufficient condition for convex interpolation, which is good news because it's pretty simple, right? Any questions? Okay, so how can we insert smoothness in that? Does someone have a hint? No? Okay, for smoothness, so one idea could be just to take convexity and to add Lipschitz gradients, right? So the thing is, this is a natural thing to do, but it doesn't work because you can construct examples satisfying this thing, but from which we'll never be able to reconstruct a smooth function. Okay? Okay, so let me say in a few words how it goes. Again, I think I will use the blackboard. Yeah, I still have a bit of time. So the two base operations I will use for that are the fact that, well, convex conjugation. Okay, if you don't know what it is, I will come back to it on the next slide. And, well, the definition of, well, one definition of strong convexity, which is the fact that, well, a function is strongly convex if and only if, when you remove this curvature, the curvature corresponding to strong convexity, it remains convex. Okay, so those are the only two things I need in order to construct the smooth strongly convex interpolation results. Okay, so about conjugation, so this is the definition, don't worry too much about it. So I think the important thing about conjugation is the fact that it's an operation that allows to switch between coordinates and gradients. Okay, so if you go, well, you take a function, a convex, well, here to be clean, I have to say convex, proper, and a closed function. Well, essentially, if you take so you take this function, you have the discrete version of it. So let's say so f, well, coordinates, gradient, and function values. When you take the conjugate of this function, essentially, what you do is you just reverse the role of the coordinates and the gradients, and then you adapt the function values. Okay, so this is essentially what it means. That so well, if you take a function f, well, the link between f and its conjugate is simply like this. Well, this thing. So this is essentially assuming, well, requiring some g to be optimal for the definition. Okay, so don't worry too much. But the important point is the fact that, well, if g is in the subdifferential, so it's essentially for smooth function, it's a gradient of f at x. Well, you have the opposite relation that also holds. It's the fact that x is in the subdifferential of the conjugate at the point g. Okay, so you really reverse the role of coordinate and gradients. And the thing is, well, it is known that when you conjugate a convex and smooth function, well, the conjugate is strongly convex. Okay, and there is a link between the strong convexity constant on the conjugate side and the smoothness constant on the other one, which is, so if you have a smooth function on this side, which has a smoothness constant L, while the strong convexity constant is 1 over L on the other side. Okay, so L here, 1 over L here. Okay, so there are some intuition for that, which are essentially that, well, when you conjugate, upper bounds essentially become lower bounds, and lower bounds become upper bounds. Okay, and conjugate of quadratics are quadratics, so it means that essentially the upper bound coming from the smoothness becomes a lower bound, and the lower bound essentially coming from strong convexity could become an upper bound on the other side. Okay, so how does it work? Let me just illustrate that on slides. Maybe on the blackboard. Maybe it will be a bit clearer on the blackboard. I will start on the blackboard, and then I will redo it on the slides. Okay, so the goal is to, so let's not talk about strong convexity because it just adds a step and it's useless for understanding. Okay, so you are given a set of points. Okay, and you want to know how to interpolate that by a smooth convex function. Okay, so we don't know how to do that, but we know how to interpolate by a convex function. So what we'll do is to try to reduce the problem of smooth convex interpolation into the problem of convex interpolation. And for doing that, we'll use the two steps I explained before. So essentially, the first step is, so this, we want to interpolate it by, let me write this for convex, set of convex closed and proper functions. Okay, so interpolable. Okay, so this set is convex interpolable. It's equivalent to say that actually, okay, let me do it. This is not what I targeted. So this set is smooth and convex interpolable. While if you use conjugation, so maybe I will at the same time recall the formulas. Okay, so I will just use those things. So I know that, well, when I conjugate, the smoothness becomes strong convexity. So I will essentially reformulate that into strongly convex interpolation result. Okay, so this set is smooth and convex interpolable if and only if another one is 1 over L interpolable. Well, convex, strongly convex interpolable. Okay, and what is this set? Well, essentially, it's the same, essentially, except that I reverse the role of gradients and coordinates. So, okay, and then I adapt the value of the objective using this thing. Okay, so xi, gi minus fi. Okay, so those are equivalent. So if you can interpolate that by a smooth convex function, it's equivalent to being able to interpolate this one by a strongly convex one. Okay, then well, you can remove strong convexity. Okay, so you can let's rename it first. Say that. So let's say that this is x tilde, g tilde, and f tilde. Okay, so this is equivalent to be able to interpolate another set just through convex interpolation, and this set is well, essentially this one when I remove the curvature, right? Let's say, let's call it mu. So essentially, it corresponds to xi tilde, gi tilde, minus mu xi tilde, and fi tilde minus mu tilde squared. Okay, let me explain it. So again, well, the only thing I use is this thing. Okay, I just use the definition of strong convexity. So here, I just said that, well, if I remove strong convexity from this one, well, I can remove without changing well, I can remove strong convexity, and the equivalent statement to this one is the fact that this set is convex interpolable. Okay, I have the impression that I may have lost some people, but let me redo it on the slides then. Okay, so if I'm given this set of points, I want to interpolate them by a smooth convex function. So the first thing I do is, well, I want to get rid of smoothness because I don't know how to handle that. So I conjugate so that it allows me to replace smoothness by strong convexity, which is easier. Okay, so now the question of interpolating the black points by a smooth convex function is equivalent to the question of interpolating the blue points by a strongly convex function. So strong convexity, well, I can just remove the strong convexity of the blue points, and the question of smoothly convex, well, a strongly convex interpolation on the blue ones, blue points corresponds, well, it's equivalent to the question of convex interpolation on the white points. Okay, so now I know how to do convex interpolation, so let's apply the mechanics. Okay, so I rename the stuff. I just apply the maximum formula we showed a few slides ago. Okay, and then I do all the steps in the opposite directions. Okay, so now I re-add the curvature, and then I reconjugate, and this is what I obtain. Okay, so this is just mechanics. I reduce the problem, well, we reduce the problem of interpolating a smooth convex function by a convex one. Okay, questions? Okay, maybe I give a few interpretations of this. Okay, so first, the final result, if you do it properly, all the steps, this is exactly, so I hope you trust me now, the formula I introduced in the beginning. If actually you remove strong convexity, this is somehow, well, inequality that is known in the literature, for example, in Nesterow's book, which we recover. But now we prove that it was necessarily insufficient for convex, well, for smooth convex interpolation. Okay, so let me give a bit of intuition on what it means, actually. So even though those conditions may appear as a bit like technical, actually, for simple example, you can check them just by looking at the examples. And in this case, for example, well, you can reobtain this inequality just by checking whether well, lower bound and upper bounds are compatible. So if you are given a discrete version of a function, which is, well, it consists of 2 points, x1 and x2, if you assume that the function was smooth and convex, well, at each point you have a lower bound of the function, okay, which is coming from convexity, okay, so those 2 black lines, and you have an upper bound because we assume that it was smooth, okay. Well, essentially, if at some point one of the upper bounds is not below the other upper bounds, well, the upper bounds, it means that this condition is not satisfied, essentially. Okay, so this is one of the interpretations. For example, in that case, the lower bound and the upper bound are not compatible, so it means it cannot satisfy this thing. Okay, so this is one interpretation. So now if we lower it, we can ensure in advance that this satisfies this thing because lower bound and upper bound are compatible. Okay, another way is, well, in fact, it corresponds to the well, let me just introduce it. So another way to interpret the construction that we just made, essentially that, well, when you are given a discrete version of a function like this, well, this condition ensures that you can take the convex hull of the upper bounds and that this is indeed a smooth convex function. Okay, so if this is satisfied, you can always do that. And it will always allow you to recover a function. Okay, so this answers a bit the question you had. This is one way to recover functions. Okay, convex hull of upper bounds. Okay, this is one. So this is actually the one which provides you with the highest possible interpolating function. Now the lowest possible one is this one, the one you obtain by just smoothing the lower bounds. Okay, and this inequality ensures that you can always do that. Okay? Okay. I'm not sure this is a good idea to go to the last point. Sorry? Because, so I propose to switch to the conclusion because I have the impression that I will just be a bit hard on the audience. Okay, so a bit of conclusions. So let me summarize a bit what I think about the methodology, and maybe after that we'll have a discussion on your opinion on it. So the nice thing is really that well, this methodology allows to guarantee, like a priori, that well, if you want to analyze your method, if the methodology provides you with unsatisfactory bounds, it means that you will never be able to improve, well, to get satisfactory bounds without adding assumption on the problem or without changing the algorithm. So if you want to obtain bounds which are better than the one we provide you numerically, it's mandatory you have to change the algorithm or the assumptions. Okay, so this is one of the nice points, I think. So there are a fair amount of generalization. So actually, this methodology can be applied to quite a lot of papers that even appear on arXiv like every day, in the optimization community at least. Now, on the bad side, well, SDPs usually, well, they become well quite expensive to solve if you want to study like complex settings. So this is one bad point. Now, the second one is that well, actually, when you want to solve analytically like semi-definite programs, usually, well, usually I'm not sure you can do it. So, well, proofs are arbitrarily complicated, and so this is not a good point. But often you can get like fair proofs by simplifying a bit the problem and by accepting not having the best one. Okay, so again, for me, tightness is only a way to ensure that the analysis provided by the methodology is not the bottleneck if you don't have satisfactory results. Okay. Okay, again, also, if you develop an optimized method using this methodology, a bad point is that actually, if you want to generalize it to other settings, since the proofs, the original proofs are complicated, it's likely that the generalization will also be complicated. Okay. But on the good side, I think that overall, it's a good way to obtain results that well, could not be verified by hand, and well, if it fits into the framework, it's also nice that you can try it without too much pain using the toolbox. Okay, so overall, the philosophy, the methodology allows you to obtain unimprovable bounds. So again, it may not be what you aim for, but it allows you to benchmark the proofs you may already have, or to know whether you can prove the result you are aiming for. So it may help in designing actually proofs. Okay, so again, the proofs that are designed using this methodology, they all boil down to a combination of inequalities. Okay, you just sum of eventually a large amount of inequalities. And I think it's nice if you want, before trying to prove something on an algorithm you don't know, well, if it fits into the framework, I think it's always nice to just plug it into the, well, in the toolbox, for example, and just check if the result you are targeting are feasible. Okay, so there are many open questions regarding to that. So for example, it's not clear how to do second-order methods. There are many problems with interpolation condition, classes of problems for which interpolation condition, well, it's not clear what it should be. And also, it's not clear if we can use that beyond worst-case analysis. Well, I have discussion with a few colleagues, well, some people on those questions, but it's really not clear how to answer them. And if you are interested, there are a few recent work we did together with collaborators I showed the picture of in the beginning. So for example, how to use the methodology for designing potential or Lyapunov-based proofs. This is joint work with Francis Bach, and we use that in particular for obtaining guarantees in stochastic settings. If you're interested in monotone operator theory and operator splitting, so for example, in the example I showed on Douglas Rashford, this was joint work with Ernest Rioux, Carolina Berkeling, and Pontus Gilsonson, so from Lund and from UCLA. Well, it's quite recent also. If you have questions on that, I would be happy to answer. And then we have a methodology which allows to, in complementary, complement to what I showed, to automatically design algorithms. So they are not guaranteed to be always optimal, but in the cases we tried, they were. And this is joint work with Yoel Drori. Okay, and if I could choose again. Actually, it was accepted in MathProg like 2 weeks ago. So it will be on, yes, the one you know. Okay, so if I could choose again 3 messages that would be happy, well, that I would be happy if you remember, let me repeat them. So the first thing is, well, for worst cases, by definition, they are solution to optimization problems. So in that case, you see that essentially this is all the base observation that allow to do what I showed. Often they are not tractable, but sometimes they are. And in particular, in the context of first-law method in convex optimization, they are. Not for adaptive method yet, but let's hope. And if you have any question, I would be happy to answer. And if you are interested, don't hesitate to check. There is like all the code I used for generating and and checking example. They are on GitHub. So feel free to try them if you are interested. And that's it. Thank you for. Yes?
So is it possible to do something with the situation when the number of iterations is bigger than the dimension?
The number of iteration is bigger than, okay, so actually the difficult setting is the other one. It's the one when the demand, oh no, you agree. Sorry, I agree with you. So for that, I don't know. So, okay, so two observations maybe. So I did not give you the worst case functions for gradient descent or for fast gradient method descent. But so if you actually go to the steps I showed in the beginning, okay, so you see that you saw that I relaxed the rank constraint condition, which was equivalent to remove the dimension, to put the dimension out of the problem. But actually, if you solve the problem, the worst case are always 1D. Like worst case of gradient descent is one-dimensional, worst case of fast gradient method is one-dimensional. So you could add a rank constraint, it would change nothing except numerical trouble. But it's not always the case, but in a lot of situations, the worst case are actually low dimension. But this is because this is fixed step. I think if you were working with adaptive method, it would not be the case. Okay? Yes?
Just interesting, you know that in non-convex case it was
So non-convex, simple non-convex case. So non-convex when essentially you have, for example, smoothness. So non-convex, people are calling it often like weakly non-convex problems. Yeah, weakly convex problems, sorry.
And in that case, you also make some interpolations?
So actually, you can also create interpolation condition for that case, and just using the same step as here. It's just the same trick as with strong convexity. So weakly convex functions, they are those are functions such that when you shift them a bit with a quadratic term, they become convex, and so you can do the same mechanics. But yeah. Thank you for the question. You had the one?
If you have, a class of functions which you can work with, so you gave a number of examples, but what if constraints are a bit more serious, like maybe graphical model type of what I was talking about, some very special type of factorization, like some of, special structures, right? You can work with this.
So it really depends on the structure you are talking about.
Do you have some examples where you would be attempting to do?
So for example, you were talking about sums. So finite sums, you can work with them without problem. But the thing is, it depends on what you want to impose on the individual functions. So it really depends on the structure. I have to say, I don't know much. Don't know how to answer in more details actually. But so for example, if you want the function to be quadratic or to want the function to be, this works also, these kind of things. But what kind of structure do you have in mind?
Well, it's like graphical model type when you have a this graph is, I don't know, planar or some special.
Oh, okay. No,
special structure.
so for example, you could, okay. For the function, I'm not sure actually. We can check that a bit. But I'm afraid that usually when you go, in those settings, actually it's non-convex, right? And so when you do a worst-case analysis on, well, maybe weekly, but usually when you do worst-case analysis on non-convex stuff, you get crappy results, right? Well, you get results, but yes. I'm not sure this is the way to proceed when you are non-convex. Other questions? Comments?
Could you comment maybe a little bit about kind of stochastic situation when, so for example, there are cases when our function is a huge sum of other functions.
Yes.
And we are not able to kind of compute it.
You mean expectation minimization, but without a finite sum assumption, for example?
Yeah.
Okay, so I can tell you, so this is, so I don't have the slides for that, but this is mostly what we did with Francis. And so actually, when you consider, for example, stochastic gradient descent, stochastic gradient, I don't like the descent, but the thing is, when you compute those kind of things, it appears, so what we do is, actually we fix the number of function in the objective, and, but when you study stochastic gradient, the worst case guarantee turned out not to depend on the number of functions. If you assume stochastic gradient, so you're not using the fact that you can compute all of them, but you still assume that there is a finite number. Well, usually the solution do not depend on that finite number. So it's a bit subtle, but we can discuss that afterwards. And so what we did is we generated we applied the methodology for some fixed number of things. We observed that the solution was not depending on it. And then, essentially it meant that the proofs were also valid for whatever number of elements. But it's a bit like a lucky, lucky guess. We tried something and we saw that it was also valid without knowing the number of elements. Okay? The question?